Morning, everybody. We'll see if my technological house of cards manages to stay up today. Oh, darn it. Of course, that's what I forgot to do. Shoot. Let's really quickly show you how to do this. I'm just going to let this play for just a little bit. Please don't panic, right? Okay. Basically, all I really need you to do is to get all your quiz sheets together and put your total number of points at the top. This does not have to be done today. Okay. Latest I will take them is next Friday, right? But you can give these to me on Tuesday or Wednesday next week. That's just fine, right? I'm not calling for them for today. But just in your notebook, right? You've been carrying these sheets around the semester. Put them all together, staple them together. Put your total score that you got. I don't need to know what it's out of. I just need to know the total score that you got, and then turn those into me. It's not going to be out of 50. I went through and I've been not giving you quizzes lately, as you may have noticed, but it's going to be like out of 30 or something. So again, don't worry about like your total score. Don't worry about what's out of. Just circle up for all the pages, write the total score on the front, and then get those to me and I can update your grade with your quiz scores. It's not meant to be stressful. All right, get rid of that. And back to this. All right. Whew. We were learning the beginning of fluids last time. And just one other thing I need to warn you about, and that is gauge pressure. The best way to describe gauge pressure is to think about tires and inflating the tires on your car. When your tire is flat, what does a pressure gauge read? Yeah, but when the tire is flat, it's going to read 0, isn't it? Is there 0 pressure in that tire? No, there's still air in that tire, right? To have 0 absolute pressure, the tire would have to have a vacuum in it, right? Like outer space. That would be 0 absolute pressure. When a gauge says 0 pressure, what's it trying to tell you? It's comparing, right? It's comparing inside to outside, okay? So gauge pressure sort of automatically takes into account atmospheric pressure, which is why we often say that the gauge pressure is equal to the true pressure minus whatever atmospheric pressure there is, right? So every pressure gauge does this, okay? Absolute is what is like real pressure, okay? And then, this is atmospheric pressure. So, and anytime you do a pressure gauge, that's what it's saying. And usually that's okay. Like you don't need to correct and know what the actual pressure in something is. It's enough to know that there is a difference, right, in pressure inside or outside or something like that. So just I warn you about that because you'll use pressure gauges in various aspects of your life. Just realize that when a tire pressure gauge reads 0, it's not 0, it's 14.7, right? True pressure. And if your tire says to inflate to 35 pounds per square inch, what would be the true pressure about? 40, it would be 50, right? Because 14.7 is about 15, right? 35 plus 15 is 50. So that would be the absolute pressure. So like if I needed to calculate for whatever reason the number of air molecules in the tire, I'd have to do that with absolute pressure. I couldn't use gauge pressure for that. All right. So that's just kind of getting the baseline down for what we need to do with pressure. Anybody know what this is? This is the Hoover Dam, right? It dams up, and Lake Mead goes in behind it. It is famously where we hide the allspark. Did anybody get? Some of you got that reference. Okay, no. But you know, the Hoover Dam is pretty impressive in a lot of different ways. But I show it to you not to talk really about the pressure on the face of the dam, like holding back Lake Mead, but rather to do a thought experiment of sorts. So if we take a look at the depth of the lake on the other side, it's like, I can't remember, 800, 700 feet tall or something like that. And if we drop a pressure gauge, right, on the water side of the dam, and we measure the pressure at the base of the dam, 700 feet below the top, we would get a pressure reading, right? On the other side, and we drop a pressure gauge down, we wouldn't get the same reading because here we're measuring in air versus in water, right? And the density of the material matters. So what if instead we just took a regular garden hose, right? A whole bunch of them, screwed them all together, right? And dropped them down the face of the dam. Plugged up the bottom, and then just started filling the top of the garden hose, right? So we're basically talking about a 1-inch column of water, right? All the way up the face of the dam. What do you think the pressure might be at the base of that garden hose from that column of water compared to the pressure on the other side? They would be the same. Pressure, right? Back on this slide. The pressure at some depth is all about, well, the atmospheric pressure pointing, on the surface of the water, plus this term right here, density, planet, and depth, right, of water column. There's nothing in there about amount of water. It's just the vertical height. So let me see if I can't, that's a thought experiment. You can't try that one. The government comes after you. Don't ask me how I know. But even if you could try it, the problem is that the garden hose would burst long before you were actually able to fill the entire thing. Why would it burst? The pressure is too high, right? Okay, that's an enormous pressure, and it's kind of wacky to think that just a 1-inch column of water could have the same pressure at the bottom as like the entirety of Lake Mead at that depth. Again, I'm not talking about the pressure on the face of the dam. I'm just talking about the pressure that you would measure at a certain depth. All right, I want to play a video here for you, okay, that hopefully will help you see this phenomenon, right, actually in an experiment in the age before CGI on a low budget. Okay.
This
so
is an electronic
what this
pressure
guy
gauge
has,
with a pressure
right, in his
sensor
hand
at the
right
bottom.
here is a pressure gauge.
Blowing into the
There's a
sensor
pressure
through a
sensor at
tube
the bottom,
increases
and
the
the
pressure
height
and drives a bar
of the
graph
display on the
whose
pressure gauge is
proportional
carefully
to the pressure at
calibrated
the sensor.
so that it will always
We'll use it to
stay,
show how the
like
pressure in a column
the
of water
topmost part of the gauge
changes with
will always stay
increasing
at the
depth.
surface of the water. Do you see that?
As the sensor goes
The deeper and
into
deeper
this
it
column
goes,
of
the
water,
longer the display
display
gets,
shows
but it's
that the pressure
always
increases
right
in
at
direct
the
proportion
surface
to the depth.
of the water.
What
Okay?
will happen to the
So
display
again, we have
if
this
tip
pressure
the water
gauge.
column at an
Pressure is a function of depth, right? So the deeper it goes, the longer the display. But they've cleverly calibrated this one so that it will always equal, right, the depth of the water in the column. So what he's going to do now is he's going to tilt this whole thing. Okay? He's going to take this whole tube right here, and he's going to tilt it over diagonally. He's not going to let any water spill out, but he's just going to tilt it over diagonally. What I want you to do, just real quick with each other, is decide. Is the length of the pressure sensor, is that red LED display going to get longer, shorter, or stay the same? Go. All right. Let's see what happens. How many of you said it gets longer? Okay, good. You're awake. Okay. How many of you said it stays the same? Yeah, some of you, and then the rest of you, or it gets longer or shorter? Shorter? All right. See what happens here. Tilts it over, gets shorter. Okay?
Tipping the
So we'll
column of
explain why in
water
a second, but I want you to
reduces the
notice
pressure
something.
reading.
Look at the
The
length of
length of
that
the display
LED
is still equal to
display.
the vertical depth of water above the sensor, as
The
shown
length
by
of
this
that
line.
display is exactly equal to the level of water in the tube. Right? Okay, so what the heck's going on here? Why did it get shorter? Pressure depends on what? The height, the depth. We call it the height of the fluid column above the point where you're measuring, right? And so when you tilt that whole thing over, the vertical amount of fluid above the sensor changes, doesn't it? Does pressure depend on amount of fluid? No, it just depends on the vertical height of the column. Now, was there actual physical water directly above the sensor? When you tilt that thing over, was there any water right here? I mean, a little bit down in the bottom of the tube, but not up here, right? It's all air. That doesn't matter, right? It's the depth. It's the difference between where the surface of the fluid is, right, and where you are measuring the pressure, okay? So, not only does it go down, right, when we tilt the tube down because we're changing the vertical depth of fluid, but that carefully calibrated sensor in this experiment changed its length to exactly match that depth, right? And you got to see that right there. So this is one of those things, it's one of those misconceptions people walk around with, that pressure is all about the amount of water. It's not. Pressure is about depth, right? It can be tiny amounts of water. You go deep, you're going to have high pressure. All right. What is... What is that? Anybody know? Car lift, okay? If you ever go to get your car serviced at a service station, get the brakes done, something like that, you might see one of these, okay? It has the ability to lift the car up using something called a hydraulic lift, okay? Or a hydraulic piston, right? So what we're going to do is we're going to lay down the law as far as it's concerned for something called a hydraulic. Okay, a hydraulic is basically a term for anything that uses fluids to pull off the following magic trick. Pascal's principle tells us that the pressure in a fluid, like if you just take 2 points in a fluid body, right? If that fluid is entirely enclosed, so not the ocean, right? Then the fluid has to be the same everywhere all the time. So what I'm going to do is I'm going to make a really funny looking container. This is not the way that like real hydraulic systems look, right? But this is an idea, right, for what's going on. And what I'm going to do is inside of this kind of funny looking tube that's got a small end and a big end, I'm going to put a really tiny piston, a plug, okay? And that little tiny plug can move up and down. And then I've got another plug. This one's much bigger on the other side, okay? And then we're going to fill, right? We're going to fill this thing with hydraulic fluid. Hydraulic fluids, ideal hydraulic fluids don't change their density regardless of what pressure you might exert on them. So incompressible things. Water is okay, but most hydraulic fluids are some derivative of a petroleum product, some kind of oil. And we're going to call the area of the plug, right, on one side, we'll just call that area 1. And we're going to call the side over here area 2. And area 2 is much bigger than area 1. All right, what Pascal's principle tells us is that if we come in and we exert, right, a force maybe down on that plug right there, okay, that we should get a corresponding force out. What's the same thing throughout the hydraulic fluid according to Pascal? It's the pressure. It's not the force. So the pressures are equal everywhere in this hydraulic fluid, but that means that we can write, so remember that pressure is force divided by area? So I can I can kind of rewrite this, right, as force 1 over area 1. And I can write this pressure as force 2 over area 2. And then I can rearrange this thing and solve for force 2. I want to know, right, how much force I can get out of one side by putting a certain amount of force into the first side. So this F2 here is going to be A2 over A1 times F1, right? This is sort of my result right here. And let's just say that area 2, I don't know, let's say it's 100 times bigger than area 1. Why not? Okay. So if I put a force, say of 10 newtons, 10 pounds, I don't care what the unit is, okay? Excuse me. If I put in a force on side 1 of 10 newtons, okay? We'll do pounds. You guys like pounds. Okay. What is the ratio here going to be if A2 is 100 times bigger than A1? Don't see it? This is going to be 100 A1 over A1 times F1. A's cancel, right? And I'm left with a factor of 100. So if we put 10 pounds in on this side, and we have a factor of 100 difference, what's the force we're going to get out for side 2? It's 1,000, isn't it? Okay, so 10 pounds going in equals 1,000 pounds coming out. This is the power of a hydraulic system. A hydraulic system lets you trade force and area by keeping the pressure constant through the hydraulic reservoir. So that means that if I need to, say, jack up my car, right? I've got a jack, right? A little rolly gig, right? And I put it on my car and I start moving the lever. Anybody that's had to manually jack up their car, right, knows that you pay a price for this ability. Like, I'm only putting in maybe 20, 30 pounds of force on every, right, push of that jack, right? But you got to do it a lot, right? Okay? Because the jack itself is only going up by like millimeters for every like huge meter long swing I do with my jack arm, okay? And pity the person has to sit with one of those emergency jacks and just rotate the darn thing, right? Okay, so I've got this long jack arm and I'm swinging this thing up and down through like a full meter, right? And the car's going, right? Because, yeah, I'm getting 100 times the force, right? 30 pounds in becomes, I don't know what my jack is, but it becomes a lot, right? I can pick up my 3,000-pound car, right, with just a little bit of force. It's just I have to go a long distance to do it, right? Okay, so I have to travel, whatever the ratio is. If it's 100, I have to go 100 times further on this side than the lift, right? So if I lift this 10 centimeters, I have to go whatever 100 times 10 centimeters is in meters. But hydraulics are responsible for like construction equipment. Okay, all of these pieces of tractors and things like that, they all run on hydraulic systems to be able to move the buckets and the arms and do the grading and all that kind of stuff. Dump trucks, hydraulic systems exist in doors, okay? I believe that these doors right here are springs. I haven't opened the mechanism to check and see how they're working. But anybody that has a hatchback car, like a minivan or the kind of back of your car that, not a trunk, but like the whole back door lifts up or something like that. You've probably, like when you opened it, heard that, right? As it slides along the things that hold up the door. Anybody that's had the hydraulic pistons in their door fail know exactly how heavy one of those doors can be, right? And so a trunk typically is just counterweighted with springs, but a big door, the springs can't be strong enough. So they'll use hydraulic pistons, right? And that little sliding sound that you hear is just the rod sliding along the piston axis. But yeah, hydraulics are everywhere, and they're really nifty mechanical systems that take us a long way. Okay, moving on. So today's lecture is just a long string of old white guy names, right? We had Pascal, now we're going to have Archimedes, and then we're going to have Bernoulli. Archimedes famous for many things, okay? The Archimedes screw, the supposed death ray, all kinds of stuff, right, that Archimedes is involved with. But I think perhaps the one that's had the most lasting impact is his principle. Now, you may or may not have heard the story. Archimedes' principle came about because there was a ruler that had a certain little problem involving a crown. Anybody heard this story? What is up with your classical education anyway? Yeah, non-existent, right? Okay. Ruler comes to Archimedes. Archimedes, smart guy, right? King, maybe not so smart. But smart enough to go to Archimedes and know that Archimedes is smarter, and says, I need to know if the crown that I've had commissioned to be built for me is made out of gold. There was some suspicion that maybe the crown was made out of lead and then just painted gold or covered in gold, right? Okay, and the craftsman made off with the weight of the gold that was now lead, whatever, right? And so, I mean, we don't know. We don't have detailed records about this, so I'm going to insert some Mr. Balogh editorial comments in here, but I imagine Archimedes was like, well, melt the thing, right? This is the first, makes sense. Melt it. If lead comes out, it was made. But apparently what the king wanted was like some non-destructive way, right? To figure out. Didn't want to hurt the crown, so to speak, just wanted to find out. And so Archimedes did what any sensible aristocratic guy in ancient Greek society would do when confronted with a problem. Does anybody know what that would be? No, he took a bath with a capital B. The Greco-Roman bath. How big were these things? Huge. We're talking Olympic-sized swimming pool dimensions, okay? And this wasn't just one person's bath. These were communal baths, right? Citywide, town-wide, depending on how big your town was, you had a bigger, smaller bath. You had a whole bunch of them. And it wasn't just a place to go swimming and clean off and all that. No, 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 no. In an age before TikTok, this was ancient Greece's Facebook. This was the social scene, right? This was the place where everybody went to discuss philosophy, wrestle in the dirt, take a swim, not smell so bad, talk about the latest, what's going on at the Met Gala, whatever's going on, right? Okay. This is the place that you went. So Archimedes went to the bath, talked to people, philosophized. And while he's sitting there, he's watching people getting in and out of the pool, right? Okay. He's not watching the people. He's watching the water level go up and down, right? And this wasn't an amazing thing. Everybody knew that if you shouted, hey, everybody in the pool, what's going to happen to the water level? It's going to go up, right? Because why? You're displacing water, right? A person jumps in with a certain volume. That volume of water needs to get out of the way, okay? And the only way it can get out of the way is by raising the surface level of the pool, right? Okay? Everybody gets out of the pool, water level goes down. So Archimedes is kind of watching this happen when all of a sudden it just hits him. The universe, for a moment, just stands in absolute clarity and everything makes sense. Have you had like kind of one of those moments where like all of a sudden you just figure something out? It happens to me every once in a while and then I like lose it right away, right? But like you just like, oh, my sister described it as the sudden rush of oxygen to the brain, right? Just that realization, you've been working so hard to figure something out and finally it like clicks, right? You're like, oh my gosh, I got it right there, right? Archimedes had one of those moments. And he got so excited, he jumped up, he started shouting, Eureka. Does anybody know what Eureka means? Yeah, not quite yippee. More like I've found it. I think of it as like a big aha. It's like the light bulb emoji, right? It's like, whoa, right? I figured out, jumps out, starts shouting Eureka, runs out of the bath, starts running down the street, shouting Eureka, Eureka. I figured it out. Only he had left something behind. Yeah, everything, right? Okay. Now, Greeks and Romans didn't have the same sort of taboos that we have in our society about naked people running down the street, but it must have been a sight, right? Okay. Old white guy streaking, yelling Eureka. It's definitely the first wardrobe malfunction in recorded history. So what was it that had set Archimedes on fire that he had figured out? This is it in its modern formulation, okay? There is a force that causes things to be supported or lifted up when they get into the water. If you jump into a pool, you feel supported by the water. We call that force the buoyant force. A buoy is an object that floats on the surface of the ocean. To buoy something up is to support it from underneath, okay? You can think of the buoyant force. Did I spell that right? I don't care. You can think of the buoyant force as the normal force for every single molecule of water that might be coming into contact with an object that is in water, right? So instead of calculating all the individual normal forces, we add them all up and we call it the buoyant force. What Archimedes had connected is that this buoyant force, this lifting up, right, of an object as it's in water, is equal to the weight of the water that got displaced by the object in the first place. We're going to write that weight as rho times g times v. That is Archimedes' principle. And how the heck, Mr. Balogh, is this a weight? What's weight? What specifically, what force? mg, gravity, right? Okay. How the heck can we draw, what are the units? What are the units on this side? It's the end of the semester, isn't it? It's a buoyant force. It's a Newton, right? So what do the units over here have to be? Newton. It has to be newtons. There's an equal sign right here. Okay. So how do we get weight to look like rho GV? What's density? It's a mass divided by volume, right? So what's another way to write mass? Density times volume, right? You keep calling it P. It's a rho. Don't make me get mad. Some of you are like, oh, I want to see that. So if we substitute this in right here, then we get rho VG. And for whatever reason, most physicists write this as rho GV. I don't know why. All right. So this right-hand side very definitely is a weight. But what is it the weight of? What is this density right here? What density would you put in here to calculate the buoyant force on an object? It's not the density of the object. Because the buoyant force is what? The weight of what? The fluid that gets displaced, right? So this density has to be the density of the fluid displaced, okay? If we want to calculate the buoyant force on a boat in the ocean, what density do we put there? Whatever the density of ocean water is, right? If we wanted to calculate the buoyant force on a balloon, do balloons experience buoyant forces? Helium balloons? Yeah, okay. So what fluid is being displaced by a helium balloon? Air. So we would put the density of air in. You getting the idea? What G do we put in? 9.8, okay? Unless, of course, Maybe we're on Venus. Why would we do that? Okay. And then what volume goes in here? Volume of what? Not the object. The fluid displaced, right? Now, some of you said object, which isn't entirely wrong. And in the examples I'll give here, you'll see, right, that I'm going to swap volume of object for volume of fluid displaced interchangeably. What must be true in order for the volume of the object and the volume of the fluid displaced to be the same? Think of well, I'd think of a water polo ball because I played water polo in high school. Think of like a basketball that's thrown into a pool, right? What does it do? It floats, right? How much of the ball is in the water? Not very much, right? That's because water is way more dense than the basketball. And so you only need a little tiny bit of water, a weight of water, a little tiny amount, right, to compensate for the weight of the basketball, right? What happens if you try to push that ball below the surface of the water? It pushes back up. Why? The buoyant force depends on what? Does it depend on the basketball? No, it depends on the fluid the basketball is in and how much of that fluid is being displaced, right? If I push that basketball down, right, I'm displacing more and more fluid, and so, right, the buoyant force on the basketball is going to increase. So but if I let go of that, what's going to happen? Poing, right? Okay. So we would do that in water polo. We push the ball down in front of somebody's chin, and it would poink. Right? Water polo is a violent sport. I became a pacifist after water polo. So what I'm trying to say is, how do you get the volume of fluid displaced to be the same as the volume of the object? You have to submerge it. Submerge, okay, or immerse implies that the object is fully surrounded. Now, if you see like a word that says partially submerged or is floating on the surface, those are all clues that the volume of the object and the volume of the fluid displaced are different. Okay, so let's do some more examples of that. The USS, we'll talk about the Enterprise. Not Picard's one, but the actual USS Enterprise, which is now in mothballs in the new version of. But the USS Enterprise was a aircraft carrier. Started somewhere around World War II, was updated through the 60s and 70s, and has been decommissioned. They're building a new one. But when it was in service, its home port was Alameda Naval Air Station in the San Francisco Bay. Okay, so it was an aircraft carrier. Aircraft carriers do what? They carry aircraft. It's in the name, right? They are a moving island, right? Like a moving airfield, right? And modern aircraft carriers carry about 7,000 personnel, okay? And they have was it 3 or 4 galleys? Those would be like kitchens and places for people to eat. 2 movie theaters, couple bowling alleys, couple of nuclear reactors, basically anything anybody would really need, right, to be on deployment for a long period of time and stay happy. I don't know why bowling alleys make people happy, but there you have it, okay? So aircraft carrier is full of aircraft and munitions and uranium and all kinds of things, right? It's asphalt on the top. It's made, the structure is steel. How much of an aircraft carrier is below the water? Not very much. Yeah. Yeah, but still not very much. It's like 1/5 of the total volume of the aircraft carrier. Okay? What does that tell you about the density of the aircraft carrier? It's less than water? What happens when something has density more than water? It sinks. And something that has a density of less than water? It floats, right? So how is it that something that's made out of uranium and people and planes and asphalt and metal can have a density less than that of water? Oh, there's air inside? Yeah, how do you sink a boat? Let the water in. I know it seems kind of obvious, right? But like, seriously, let the water in. Because a boat that's full of air is displacing a lot of water. If you let the water in, now you're only displacing the volume of the structure of the boat, and there isn't nearly enough buoyant force for that to happen. So what does that tell you about a submarine? What is the density of a submarine if it's floating there below the surface of the ocean? It's the same as the fluid around it. If it's going down, it's got to be denser, and if it's going up, it has to be less dense. How does a submarine change its density on the fly? Ballast tanks. These are dedicated structures in the submarine that are either filled with water or filled with air. If you fill the ballast tanks with water, which way is the submarine going to go? Down. Okay, you're letting water into the, not where the people are, for those of you who are concerned. But if you then blow that water out using compressed air, what happens to the density of the sub? Decreases, and so which way is it going to go? It's going to go up. Now, submarines have other ways to do this. They have dive planes, and they have propulsion that makes it more efficient to do this. But they can just move vertically in the water column if they need to. What's the density of a fish? All fish, everywhere, all the time? It's the same as whatever fluid they happen to be in, right? Okay. How do you know? They're not rising or sinking in the column, right? Okay. A dead fish? What do dead fish do? And then eventually they float, okay? Why are they floating? Yeah, they're less dense than water. They're full of gases from the decomposition, right? So yeah, all of this is happening. So how do we like kind of conceive of everything that's going on here and really get it down? Here's some water, right? Here's an object. It could be a boat, could be a log, could be a fish. Hopefully not, that would be a dead fish, right? If it's floating, what do we know? There's nothing new there, right? Why is there a horrendous delay? Oh, it's not that bad. It's not that bad. It was there for a second. It's gone now. What do we know? If something's floating on the surface of water, what do we know about the weight of the object and, darn it, the buoyant force that's acting on it? Why do they have to be equal? Because floating is a static situation. Is anybody having flashbacks from chapter 12? Okay? Floating is a static situation, right? Don't need to worry about the horizontal because we're not moving anywhere. We're just talking about, right? And so as long as the buoyant force and the weight of the object are the same, you have a floating object. Can something be floating under the surface of the water? Yes, right? Because floating is a static equilibrium condition, right? So with this set up like this, we can take a look at this idea right here, right? Okay, buoyant force on one side, weight of the object on the other. Well, we already know that the buoyant force is equal to the density of the fluid times g times the volume of the fluid, right? Buoyant force is all about the fluid that got pushed out of the way. We can write the weight of the object, not as mg, but using this trick up here that we developed, we can go ahead and write the mass as density of object times g times volume of object. What cancels? The little g can't, but what does that mean? What's the implication of that going away? We just solved the problem of floating everywhere. You want to float in the clouds of Jupiter? I've got your answer. You want to float in the clouds of Venus? I've got your answer. The clouds of Titan. Why do I keep saying clouds of these different planetary bodies? Titan, Jupiter, Venus, they all have something in common. Clouds. An atmosphere thick enough to suspend a balloon, let's say. NASA has been figuring out how to get spacecraft to land in the atmosphere of Venus. The atmosphere of Venus is so thick and has such high pressure at the surface that devices and people and spacecraft, they don't like it down there. Okay, there's acid rain, there's lots and lots of pressure. We're talking like several hundred times more than atmospheric pressure on the surface of Earth. But if you get high enough, there's a point in the Venetian atmosphere where the pressure is the same as that on Earth. The temperature is just a little tiny bit cooler than that of a normal day average on Earth. Okay? The only problem is a lack of oxygen. It's mostly carbon dioxide and sulfur. So there's plans to try to send a spacecraft to Venus, have it park in the atmosphere by inflating a balloon and riding in that place of perfect habitability by humans and anything else, right? First send robots, then send humans. Have a good time studying Venus. So we can do it, and this is how we do it. What's that? Cloud City. Let's do it. It's just they did that wrong. It needed to be balloons. All right. Not very defensible if it's a balloon, but you get the idea. What do we got? Density of fluid, volume of fluid equal density of object, volume of object. In order, we'll put a box around it. I tend to write it somewhat differently. That's right. So in order, right, for volume of fluid and volume of object to be the same, what has to be true about the densities? They have to be the same, right? There is an equal sign right here, okay? Right? Now, what happens if the volume of the object is, what happens if the density of the object is smaller than the density of the fluid? The volume of the object, so like, what I tend to do, because this is a little bit confusing to me, is I tend to write a ratio, volume of object to volume of fluid, right? So if I solve for that, right, if I take my volume of my fluid and I divide both sides, and then I divide both sides by the density of my object, right? I get density of fluid divided by density of object, right? So this might be a little bit more confusing, right? But it just depends on how your brain wants to read it, right? If the density of my fluid and the density of my object are the same, what is this number over here? Just a big fat 1, isn't it? Which means the ratio of the volume of the object and the volume of the fluid has to be 1, right? In other words, it has to be the same, okay? But what if the volume of my object is less than the density of my fluid? What is this ratio now? If this is small and this is big. This is a number that is greater than 1, right? Which means that the volume of my object to my fluid is also greater than 1, which means not all of my object is in the water, right? Okay? And if the density of my object is bigger than the density of my fluid, this is a number that's less than 1, right? Which means this ratio is less than 1, which means I'm sinking. Like, I can't get like less fluid than the volume of my object and have this work, okay? Solve the thing in the box however you want for what makes sense to you. But what the thing in the box tells us is if your density is the same, then the volume of fluid displaced and the volume of object are the same. And if your density of your object is smaller than the fluid, what's going to happen? It's going to float with some amount of it above the surface. So if the density of your object and fluid are related, like let's say the density of your object is half the density of the fluid. How much volume of the object will be below the surface of the water? Half. Yeah. Icebergs with penguins or polar bears on them. You choose the hemisphere, okay? The common wisdom is that what? 90% of an iceberg is below the surface of the ocean, and only 10% is poking it above. What do you instantly know about the density of ice in the ocean? It's less than that of water by how much? 90%. If 90% of the volume is below the water, that means that the density of that iceberg is 9/10 the density of seawater. This concept and idea has been enshrined in a term called specific gravity. What is the density of water, like numerically? Anybody know? Chemists? No? Don't want to admit it? It's 1 gram per cubic centimeter, which are the wrong units. Why are they the wrong units? Because it shouldn't be grams, it should be kilograms, and instead of centimeters, it should be meters, right? So we convert, and it turns out this is 1,000 kilograms per cubic meter. Those are the same thing, okay? That's the density of water. The specific gravity of a substance is the ratio of its density to water. In other words, if you have something that's got a specific gravity of 0.6, then what is its density? It shouldn't be that hard. 0.6 times 1,000 is what? 600, right? You instantly know that it's 600 kilograms per cubic meter. What if its specific gravity is 1.5? What's the object's density now? 1,500 kilograms per cubic meter. Or if you want, 1.5 grams per cubic centimeter, right? Specific gravity is a quick way to just basically reference to waters. Now, seawater is not this. Salt water is different. Why is salt water different? It's got salt dissolved into it, right? So it's going to cause other, it's like 1,050, 1,020. It varies, by the way. The salinity changes wherever you, by depth and temperature and a bunch of other things. But we reference everything. And by the way, the density of water we picked. You can measure it, sure, but we define the density of water as 1,000 kilograms per cubic meter. And then everything else's density is referenced to that, right? So density of aluminum, density of helium, they're all referenced to that of water. So let's do some examples here. Let's not do that one. Let's do just to show you, come here, that it does work.
We'll use these three
Right.
blocks of wood
So
to
they've got three
demonstrate
different
how
kinds of
density
wood here,
affects the depth at which
right?
objects float.
And they all have
This
varying
block
densities.
is cut from balsa wood
Okay.
with a density
I
of
think that's
about
balsa
0.14
wood, right?
grams per
It
cubic
has a
centimeter.
density in the wrong
When
units of
placed in water,
0.14
It
grams per
flows
cubic
with
centimeter.
only about 1/7
right?
of its volume
about, what is
submerged.
that, 20%-ish
This is a block of
below
pine
the water? That's pine.
with a
Pine's
density
like
of about
half,
0.5 grams per
okay?
cubic centimeter.
And so half of the block
It
stays
floats
below
with
the
about
water.
half of its
This last
volume
one they're going to put
submerged.
down is called ironwood.
This is a block of
and it has a
ironwood
density of about 90%
with a density of
that
about
water,
0.9
and so
grams per
9/10,
cubic centimeter.
right, of
When
its
placed in
volume
water,
is below
it
the
floats
water.
with
So
about
anything that
9/10 of
goes
its volume
over
submerged.
1,000 kilograms per cubic meter, specific gravity of 1 is going to do what? It's going to sink, right? I do want to show you, I've got time. I want to show you a video, okay? I don't want to show you the video because of what the video teaches. I've showed you a lot of these clips through this entire semester, haven't I? Okay, of various physics experiments that have been going on. And I've kind of teased the people in the video because they're very Very serious. This is science. Serious. No smiling. No smiling, right? The video series these comes from is called the Encyclopedia of Physics Demonstrations. It's a 24 DVD set. And on each DVD, there's about anywhere from 15 to 30 of these demonstrations. Okay? And I've only picked a few because most of them are not good. I've watched all of them. Right? I just, to be a good teacher and to have media and all this kind of stuff, I know they're old and nobody's really done any sort of similar thing in the modern age because it doesn't get the views. But I've watched all of them, and every single one of them, straight, science, serious, no smiling. Watch this. The video is about
We're used
the
to
idea
seeing
about how
objects
much
floating
water
in
does
large
it take
amounts
to
of
float
water.
something.
But
Right?
how much water
And
is
the answer,
actually
unsurprisingly, is
required
that
to float
it's
an
not
object?
very much, right? So
We'll
they take this
use
2x4
this
and they
wooden
have
block
a
to
little
find
tiny
out.
container. They put just
This
a tiny
container is
bit of
just
water,
barely larger
right,
than the
in the
block
bottom, and they're
has
going
a
to show
small
us
amount of
that
water in the bottom.
you only need just a
When
little
the
tiny
block
bit
is
of water
placed
to float
inside,
something, right? It's not the
the
amount
small
of
amount of
water,
water is
it's
enough
the
to
density
float
of the
the
object
block.
that really matters. So now they're going to
The
switch
amount of
to
water
an
required to float
animation
an object
that's going to
is
help us
just enough to
understand
actually
how boats
surround the
float.
object in
I
its
want you to watch
container.
very carefully the stern of the ship.
In a container of the right
Watch it.
size,
Watch
a
it.
large object, such as this ocean liner, could also float in a small amount of water.
What just happened? I kid you not, right? For untold hundreds of these videos, there's nothing going on, and then all of a sudden in that one, they go dark. I think this is the editorial and animation department cracking under the strain of having to just be a serious. It's weird. There are Easter eggs everywhere. Okay, let's do an example. Maybe. Come on. You can do it. All right. Hey, look, Archimedes is back. So we have an unknown density object, right? And we're going to find out what the density of this object is. On the way, we'll find the volume, but we're going to find the density ultimately so we can decide whether or not this crown is made out of gold. What do we know? Well, we know the weight in air, right, is equal to 300 newtons. So by the way, I should warn you, when a physicist says something like weighs a certain amount in air, we tend to have a very specific picture in mind, and it's a bit old-fashioned. I don't know if you've ever been to the supermarket where they have one of those scales that's hanging underneath the dial, right? And you put your thing in, and it goes sideways, tells you how much it weighs. We don't do that hardly ever anymore. The scale now is built into the laser scanner. You set it down, it weighs something, right? We tend to think of weighing an object in air as dangling it from a hanging scale, right? If I were to attach this object to a string and attach that to a scale, the string's tension would be 300 newtons, right? It's okay to think of it as a standard scale with the normal force of the scale holding up, right? But sometimes you come across a problem and you're like, how is this thing weighing anything if it's just dangling, right, from a string? Well, the answer is, right, okay? Think of they're reading the tension in the string, right, is what's going on there. Anyway, so the weight in air is 300 newtons, right? And then the weight in the fluid. So this is kind of weird, right? So apparently there's some container. It's filled with this fluid, and the object is being put in here, right? And they're weighing it. Well, a lot of containers don't have scales built in. So again, it's kind of like they're taking a measure of this tension, right, that's acting up on the object. Of course, the weight's acting down. Does gravity change simply because we put this thing in a fluid? No, right? Weight is weight. Force of gravity is going to be the same no matter what, right? But the thing that's changing is the tension in the wire. And why is the tension changing? The scale's reading, because there's a buoyant force that's also acting up, right? So over here, the tension is just equal to the weight. But over here, tension and buoyant force acting upward are going to be equal to the weight acting downwards. I am sort of skipping the step where I write like T minus mg over here, 0 equals T minus, and over here I would write 0 equals, what would that be? T plus B minus mg, right? We've applied Newton's second law enough that hopefully you were with me on that one. So if the weight in the fluid is 200 newtons, right? And the only difference between this equation and this equation is the buoyant force. What must the buoyant force be? It's got to be 100 newtons, right? The weight didn't go anywhere. What happened is a buoyant force got involved, right? And so the difference between the weight in air and the weight in the fluid has to be brought about by the buoyant force itself. All right, well, if that's the buoyant force acting on the object, and that has to be equal to the density of the fluid displaced times g times the volume of the fluid displaced, right? We can do some kind of interesting thing. What can we solve for here? What's not known? We know 100. Do we know the density of our fluid? Yeah, it says specific gravity of 0.7. So what is the density of our fluid? It's 700 kilograms per cubic meter. Okay? All right, so we got that. Do we know what planet we are on? Do we know the volume of our fluid? No, but we can find it, right? Volume of fluid is the only unknown thing in this statement, isn't it? So if I take my buoyant force, 100, I divide it by 700 and 9.8, right? And because I put standard units into everything, I should get standard units out. What will the standard unit of volume be? Cubic meters, right? And so I do this, maybe, yeah, did I do it? Oh, I did. I got 1.46 times 10 to the minus 2 cubic meters. Okay? So there's my volume of the fluid that got pushed out of the way. How do we find the volume of the object? There's a clue in the problem. Starts with an I, ends with immersed. Immersed. What does that word mean? Completely in the fluid, right? So if this object is completely in the fluid and it's pushed away 1.46 times 10 to the minus 2 cubic meters, what do we know? We know the volume of the object, right? You push an entire object below the surface of the water and it pushes away a cubic meter of water, you know the volume of that thing is cubic meter, right? They have to be the same. So again, that only works if you're completely surrounded by the fluid, right? So that means the volume of my object is 1.46 times 10 to the minus 2 cubic meters. And to find, which is one of the things they wanted me to find, so I put a box around it. The density of my object is going to be the mass of my object divided by the volume of my, but where's the mass? I don't have the mass of my object. We know the weight in air, don't we? And we know what weight is, right? Weight is equal to mg, so m is equal to the weight divided by g, so that's 300, that was supposed to be a 3. 300 divided by 9.8 got me 30.6 kilograms. And now that I know it's 30.6 kilograms, and I know it's 1.46 times 10 to the minus 2 cubic meters, I know that this object's density is 2.1 times 10 to the 3 kilograms per cubic meter, which is close enough to gold to say it was made of gold. We actually don't know. The historical record does not tell us anything about the result of Archimedes' wardrobe malfunction. But it does record that the question was asked, or at least that's how it's been handed down throughout history, because as we all know, history is determined by the victor. All right. I'm going to skip that one. Aha! Why would anyone propose the idea of putting a broadband antenna on a balloon and floating it above a populated area in order to deliver internet service? Cheap? BBC News. Broadband net goes stratospheric. Airships in the stratosphere beaming back broadband seems like a fantasy, but tests in Sweden have suggested it become reality in 3 to 5 years. A successful trial of the technology is conducted by researchers led by the University of York in the UK. Trials using a 12,000 cubic meter balloon. More on that later. Flying at an altitude of around 24 kilometers for 9 hours proved to successfully operate the data link rate, blah, 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 blah. This article was published on October 19th, 2005. Are there any Zeppelins flying around delivering us internet? No. What happened? What happened was LTE. All right, prior to this, it was 2G and then 3G, and things were pretty slow on the cellular phone side, okay? The Apple iPhone was sort of a brand new idea back then in that time frame. And what happened is that the ground-based technologies for transmitting cellular service became way better, way faster, right? And the need for floating things in the air. It would have been cool, but it just wasn't as feasible. But what we're going to do is we're going to calculate the what if, right? What we're going to do is we're going to find out how much helium we need in order to just float a broadband antenna, the kind of antenna you would see on the top of maybe one of those big cellular towers, okay? So I went and I looked up sort of like the industry standard for something that can deliver, like, I think at the time I was calculating this, it was like 800 megabits per second. So 4,000 kilograms was the answer, 4 metric tons, okay? Then I went and I looked up manufacturers of balloons that can hold up 4,000 metric tons, right? And those manufacturers were suggesting that you needed a balloon, just the material of the balloon. So just and this is what these balloons are made out of, okay? This is, I think, was this polyethylene plastic, okay? It's really, really thin stuff, right? But it's really, really strong. It actually takes quite a bit of force to like puncture it, okay, or tear it. So this thin material like this, right? You need 600 kilograms of this. How big is this balloon going to get? It's going to get big. So let's calculate, right, how much helium we're going to need, right? So free body diagram. Whoops. That is the power grid. You guys don't want to see that. Well, you probably want to see that instead. So let's see. Here's my balloon, okay? Name all the forces that are pushing or pulling on the balloon if it's just floating there at the launch pad. So, okay, gravity. Weight of what? Okay, so there is the weight of the balloon's material itself, right? The envelope of the balloon, all that plastic, right? The 600 kilograms. What else? What's hanging off the balloon? The antenna, right? So we're going to have mass of the antenna times g. Buoyant force, right? Of course, we're filling up a balloon full of helium. Helium's lighter than air, so it's going to be lifted up, right? We're missing one thing. It's in plain sight, and it's really easy to miss, and it's one of the reasons I'm doing this example. It's the weight of the helium inside the balloon. Does the helium itself have weight? Yes. Does it need to be supported by the buoyant force? Yes. So don't forget about the weight of the helium. Now, I've written all those weights as m times g, right? We have buoyant force acting up. So if we do 0 equals all these things, that's buoyant going up minus mass of the antenna times g, mass of the balloon times g, minus mass of the helium times g. Okay. I don't see a volume of helium anywhere in this statement yet. Where's the volume of helium hiding? It's hiding in two places. So yes, it's hiding in the buoyant force, right? Because the buoyant force is the density of what? Careful. The air. Why is it the density of the air? That's what is getting pushed out of the way, right? This balloon is in air, and so the displaced fluid is air, not helium. Helium's doing the displacing. Okay, times G times volume of balloon. Didn't spell that right. V sub B. Okay. Minus mass antenna times G minus mass of balloon. So mass of antenna times G, mass of balloon times G, both of these right here are numbers, right? We can calculate those right now if we wanted to. They're just along for the ride, so I'm not even going to switch them. Now, what about mass of the helium? Do we know the mass of the helium? No. But we know that mass is equal to density times G times V, don't we? Because of what we did on the other slide. So mass of helium would be density of helium and volume of helium. So I could write this weight term for the helium right here. I can write it as density of helium times G times volume of helium. But what's the volume of helium? It's the volume of the balloon, right? The balloon, is it completely immersed in air? Yeah. And so this volume of helium is equal to the volume of the balloon. So, what's the thing that's the same in all of these terms? What did we just do? Solved it for Venus. We can put internet on Venus. So this is density of air times volume balloon minus MA minus MB minus density of helium times volume of balloon. What are we solving for? Volume of the balloon, because that's going to be the volume of the helium, right? So let's see. To do that, we move the volume terms over. That's density of helium, volume balloon, minus density of air, volume balloon equals, why did I do it that way? Don't do math the way I do math. Come here, go away. There we go. I'm going to move the masses over, because they're both negative, and leave my densities and volumes alone. Factor out the volume of my balloon, and then divide this side, right? I'm going fast. This will be mass together divided by density of air minus density of helium equals volume of my balloon. Antenna, 4,000. Balloon, 600. Density of air, 1.2. Density of helium, 0.179. Put it all together, and we get a volume of 4.14 times 10 to the 3 cubic meters. 4,000 cubic meters of balloon. Let's see. This room is approximately 10 by 20. What's 10 times 20? 200 times 3. 600. Okay. So 1, Yeah, about 3. So let's see. This room has a volume of 600 cubic meters. The balloon we're after is 4,000 cubic meters. So we would need, what is that, 5.5 classrooms this size? Just to float the balloon at the launch pad. Right? Crazy making? No. This is the balloon that carried Felix Baumgartner to the edge of the stratosphere. Felix Baumgartner became the first person to ever skydive from that height and break the sound barrier during free fall on the way down. No plane required. What was required was a balloon and a gondola to carry Felix all the way up. Took him 6 hours. It was kind of boring and pretty cold. Okay. He's in a sort of a spacesuit type thing. Okay. There it is floating up. You can see it's kind of partially deflated. You can't inflate these balloons to their fullest at the launch pad because as they go out, what happens to the density of the atmosphere? Gets thinner. And so the balloon is going to expand. At its full expansion, it was approximately the same height as the Statue of Liberty, which means nothing to us because we're from the West Coast, right? But these kinds of balloons are used fairly frequently, not just to do Red Bull stunts, but to carry scientific payloads up to these heights, right? In order to conduct scientific research or spying or whatever it was the Chinese were doing that we shot down, right? Okay, that sort of thing, right? So that's fluid statics, right? Playing around with the buoyant force and doing a static equilibrium problem. On Tuesday, you're going to give me quiz sheets, right? Talked about that at the beginning of class. We're going to finish chapter 14 by doing fluid dynamics. Okay? Which gets more fun. And by fun, we spell that P-H-U-N, which means it gets harder. But that will be the last lecture of Physics 4A. Right? Yeah, I know, it makes me sad when everybody cheers. Okay, I understand, I completely do. I will see you then, right, for the end of class, and then we'll take our exam.